there are only two simple math functions, that's not the right word, operations, which commute, what are they? Where the order does not matter.
Addition.
And
Multiplication.
those are the two. In this case, multiplication is the one, so I'm gonna have Q1, capital or lowercase, depending on your mood. There's also, distance seemed to have some effect on it. Again, the leaves don't seem to be doing much, but the closer I get, the more that they will spread. So there does seem to be some connection with distance. So as R gets smaller, the force gets bigger, so that would go in the denominator, and it's squared. And the experiment that we'll do on Wednesday of this week, you'll be checking to see, is that really 2? And the only other thing left is just, well, sorry, not the only thing. The last thing for the magnitude is a factor up front. And sometimes I will write K sub C, not E, but C, depending on my mood. This has two names, and thus the two different subscripts. This is either the electrostatic constant, or Coulomb's constant. Units of force, SI units of force.
Newtons.
Say it again.
Newtons.
Joules.
Say it again.
Newtons.
Oh yes, newtons. Joules is entered. Unit of distance, SI unit of distance.
Meters.
Charge.
Volts.
No. We'll get to volts eventually.
Electron volts.
No, that's unit of energy. The unit of charge, the SI unit of charge is the Coulomb, capital C. And anyone want to take a wild guess who it's honoring? Exactly. It's like you've done this before. And so if you work that out, the units of the electrostatic constant are Newton meter squared per Coulomb squared. Let's parallel that. Want that one. What is the generalized gravitational force formula? Generalized.
K G times M1 times M2 over R squared.
Yep, there you go. mg you could consider generalized if you know what the value of little g is, but what is the acceleration due to gravity of the Earth relative to the sun? I would use this. Notice the similarity between the two. They're both 1 over r squared relationships. They both have some special quantity times themselves and some constant up front, and that's basically where the similarities end at the moment. Well, that's where the similarities end. When I was in grad school, I had access to a proposal for the South Carolina Department of Education high school graduation requirements. And one of the high school graduation requirements that was in the proposal was to express the electric force in terms of the gravitational force. Now, I think the intent was to recognize they're both 1 over r squared relationships. However, the way it was worded, as my advisor said when I told him about this, he said, well, not only would you graduate from South Carolina High School, but you'd win a Nobel Prize. That if you could figure out the better connection between the two, instant fame. Probably a Nobel Prize, so $1 million there too. So let's actually look at the difference between the two. So why don't we start out with, sorry, before I get too carried away with myself, what's the thing that we're missing from the equation over there? What's missing?
Units.
Unit? No, we have it in terms of variables there.
Direction.
Yes, we are dealing with a vector. I know that if they are opposite signs, I'm gonna end up with a negative value here. So that means I need some sort of relationship indicating towards some central point, or charge 2. And so we throw in an R2 hat. The radial unit vector. R2 hat is away from the center, and if this quantity here is negative, then that means, it's the opposite way, it's towards. So it's towards 2. So let's take a proton and an electron. And I want to know the force, the electric force on the proton from the electron. Well, K, that constant, 9 times 10 to the 9th Newton meter squared per Coulomb squared. That is sufficient. Some people don't like rounding it off like that. It's 8.99. And if you want to keep going, there is a very precise formula for it. It doesn't come up, it's still an irrational number because you're doing a square root in there. But you can get far more detail, and in the lab that you'll do on Wednesday, I have it listed in there out to 10 places. All right, times the charge of an electron or proton. Charge of the proton is positive, charge of the electron is negative. And we can write Q of the proton is equal to E. The charge of an electron is equal to negative E. This is not Euler's constant, the 2.71828, etc. This is considered to be sort of that base charge. 1.6 times 10 to the negative 19th coulombs. And that's rounded off. So the charge of the proton, 1.6 times 10 to the negative 19th coulombs. Charge of the electron, negative 1.6 times 10 to the negative 19th coulombs, divided by the distance between them. So let's put the distance between them to be 0.5 meters. So 0.5 meters squared. If someone would be kind enough to talk of our electron. Now, if you don't have your calculator here, I do recommend that you do this at home just to make sure you get the same value. At this level, generally not an issue, but occasionally run into people who mess up with the times 10 to this.
Negative 9.216 2 times 10 to the negative 48. Yes.
Minus the
Meter squared.
Pardon?
Meter squared.
No, but you did hit on what's missing. What do we find? There's 2 things missing, really, but Yeah, just newtons, all right. And what's the other thing that's missing?
Direction.
Yep. There we go. Questions? This next question I've asked on tests before. Shocked at the number of people who missed them. I have a proton here, I have an electron here. Distance between them is 0.5 meters. We just went through that problem. I'm now going to put another proton over here, proton. 0.5 meters on the other side. It's just, so we got 9.2 times 10 to the negative 28th newtons. There, for the magnitude, what's the total force on the electron? Now, before you board it out, just think for a moment, because there's a trap that some people fall into. Total force on the electron. All right, here we go. In unison. 3, 2, 1. That was,
0,
what'd you say?
0,
And
I'd say 2.
you say 2?
Yep.
So we have 0 and 2.
0. 0.
Is physics by democracy valid here? Yes, it is. How'd you come up with 2?
2 forces, like I'm assuming they're equal forces, the protons. So equal in each direction, but then it would have no.
Yeah, some students will go through, they'll plug and chug into here, they'll get the negative 9.2 times 10 to the negative 28, and then they'll double it. Why does that not work?
Is it just because of the direction again?
Where's the direction reflected in this?
Towards the,
left direction.
Towards the electron.
Yeah, towards the electron. So, if we worked it out the long way, we'd have negative 9.2 times 10 to the negative 28th R, I'll just call this 1. P1 plus negative 9.2 times 10 to the negative 28th R P2. And when adding these together, you need to have a common reference. This is in reference to proton 1, that's in reference to proton 2. They are in opposite directions. So what you have to do is figure out at the point in question, such as right here, the point in question. We'll just make that I hat. I know that our P1 is going away from P1. And so at this point, it's in the I hat direction, so this would be negative 9.2 times 10 to the negative 28th I hat, plus, at this point right here, I hat is heading towards P2, so that would be, so negative RP2 is I hat, plus 9.2 times 10 to the negative 28th I hat. So when you're going through this, often it's really convenient to do it from just to think through the directions, and but there are times when you have to pay strict adherence to the math. So if you're going to go the math route, please be very particular. Now, questions up to here before we answer the other burning desire that each of you have? Where's the calculus? Questions? you have had E&M before? Okay. Infinite line of charge with a linear charge distribution of, well, we'll just keep it of, with uniform linear charge distribution. I have another charge sitting right here, a distance L away, and this is charge Q. We'll make it PQ. What is the force on big Q from this infinite line of charge? Some issues in the past of students constantly wanting to plug into the Coulomb's equation when you have a distribution. Typically, when you have a distribution of charge, calculus is going to be involved. Now, there are some shortcuts that we'll get into, but for right now, if you see a distribution of charge, your mind should immediately switch into, wonder if we're going to have to use calculus here. So the way that you tackle these problems is that you take some small little segment here, which I'm going to call d little l, and I'm going to look at the force between this small little segment of charge and that charge, and then integrate. Now, if not told, assume it's positive. So this is being forced in that, there's a force in that direction. This is some angle of theta. And I'm going to label that x. So let's just make that x equal to 0, and this is, yeah, I'll leave it at x. So I got a force that's acting up at an angle there. Let's take it piece by piece. This is a point charge here. Assume that that's a point charge, and this is definitely a point charge. It's a differential, which is infinitesimally small. Really hard to come up with something other than that's a point, which is also infinitesimally small. Charge density is charge per length, or dq, dl, or dx in our particular case. It's uniform, so the differential is constant. So I know that the force on Q from the line is going to be equal to Coulomb's constant times Q times dq, that should be df, over r squared, r dq at distance there is r. All right, so you pick a small differential, you look at the force from that small differential, and then go from there. Well, first off, we've got this bit right here. It's going to change. It'd be helpful if we can get it in terms of something common. R is going to change. R hat is going to change. So these are variables. We need to get it in terms of the same variable. So first off, I'm gonna bring in my theta there, which I established as that angle. So KQ DQ over R squared times I hat J hat cosine theta I hat plus sine theta J hat. Doesn't necessarily look better, but it is actually. So I have this triangle there, the hypotenuse of R, far side is L, and the bottom side is X. What is the cosine of theta?
X over the distance.
Which one? Use X over the distance.
Between DL and Q.
Okay. So we end up with KE Q DQ over R squared times X over R I hat. And sine of theta?
Y over R. Or L?
L in this, wait, look here. L over R, J hat. So now I've got, well, let's look at the I hat part first. So F X is going to be equal to the integral of KEQ DQ d little q over R squared X over R I hat. Or writing it out in perhaps in simpler form. KEQ, those are constants, times the integral of X dq